Right now, as you are watching this, the ground beneath millions of people is breaking apart in 3 separate corners of the planet at the same time. Venezuela recorded a magnitude 5.8 earthquake this week that sent residents in Caracas running into the streets at 3 in the morning. California's Salton Sea region just logged more than 40 separate tremors in a 72-hour window, the highest seismic stress reading in that zone in 11 years. And Japan, which had barely finished counting the damage from its January 2024 magnitude 7.6 disaster, just absorbed a fresh magnitude 6.1 aftershock that rattled the Noto Peninsula and triggered new landslide warnings. This is not a coincidence of headlines. The United States Geological Survey published a seismic stress update this month, flagging elevated activity on 2 of the country's most dangerous fault systems simultaneously. And Venezuela, California, and Japan were not the only places shaking. Turkey, Greece, and the Philippines all registered significant seismic events inside the same 7-day window. Something significant is happening across tectonic systems right now. Today we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt the ground move beneath your feet? Tell me where you were, what you were doing, and how long it lasted. The people reading the comments section right now want to hear your story. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one, so the algorithm actually shows it to people who need to see it. Now, let us get into it. Start with Venezuela. Most Americans think of Venezuela in terms of its political crisis, its oil reserves, its economic collapse. Very few people think about the fault system running directly underneath its capital. On a Tuesday morning in early July, at 3:18 in the morning local time, residents of Caracas were jolted awake by a magnitude 5.8 earthquake. The epicenter was located approximately 47 kilometers to the north-northwest of the city, at a depth of just 10 kilometers, shallow enough that the shaking reached the surface with almost no attenuation. Shallow earthquakes are the dangerous kind. The deeper an earthquake sits, the more the energy spreads outward and dissipates before it reaches the surface. A magnitude 5.8 at 10 kilometers depth hits harder than a magnitude 6.2 at 60 kilometers. That is not opinion. That is basic physics. Buildings in Caracas shook for approximately 22 seconds. That is not a long time in human terms. In structural terms, 22 seconds of ground acceleration is enough to crack unreinforced concrete, collapse older brick walls, and send anything stored overhead crashing down onto sleeping residents. Reports from Venezuelan civil defense authorities confirmed structural damage in several older residential districts. Power was cut in 3 municipalities for several hours as transformers failed. The National Seismological Agency logged 14 aftershocks within 12 hours, the largest registering at magnitude 3.9. What makes this event particularly significant is not the magnitude alone, it is the fault it came from. Venezuela's northern coast sits directly on the boundary between the South American plate and the Caribbean plate. That boundary has produced some of the most destructive earthquakes in Venezuelan history, including the 1812 earthquake that leveled the capital and the 1967 Caracas earthquake that killed more than 200 people and destroyed hundreds of modern apartment buildings. The fault is active, the fault is loaded, and Venezuela's urban infrastructure, built over decades with limited seismic codes, limited enforcement, and a construction boom that preceded the country's economic collapse, is among the most vulnerable in the Western Hemisphere. Now let us go to California. California is the most seismically surveilled piece of real estate on the planet. Thousands of sensors, hundreds of monitoring stations, and decades of USGS and Caltech research mean that when California shakes, we know about it within seconds and understand it within hours. What happened in the Salton Sea region this week is not a mystery, but it is a warning. Over a 72-hour window beginning July 8th, the Salton Sea seismic zone registered 43 individual earthquakes. 31 of them were below magnitude 2. Too small to feel, detectable only by instruments. 7 were between magnitude 2 and 3, producing a brief rolling sensation for anyone nearby. 4 events crossed the magnitude 3 threshold. The largest clocked in, at magnitude 3.7, felt as far north as Palm Springs and as far south as El Centro. That does not sound alarming on its own. Earthquake swarms in the Salton Sea zone happen regularly, but seismologists at the USGS flagged this particular swarm for a specific reason. The stress accumulation reading on the southern end of the San Andreas Fault, the segment running from the Salton Sea northward through the Coachella Valley toward San Bernardino, reached its highest recorded level in 11 years following this sequence. The southern San Andreas has not produced a major rupture since 1857. It is considered, by most seismologists who study it, to be the most overdue major fault segment in the United States. Every swarm in its vicinity is watched closely, not with panic, but with very careful attention. And then there is Japan. Japan's relationship with earthquakes is unlike anything else on Earth. The country sits at the junction of four major tectonic plates: the Pacific, the Philippine, the Eurasian, and the North American, and it records more seismic events per year than almost any comparable landmass on the planet. The Japanese government estimates that 18% of the world's highest magnitude earthquakes in the last century have struck within or immediately adjacent to Japanese territory. But knowing that history does not make each new event easier to absorb, a magnitude 6.1 earthquake struck the Noto Peninsula in Ishikawa Prefecture, the same region devastated by the January 1st, 2024, magnitude 7.6 earthquake. That disaster killed more than 240 people, collapsed thousands of homes, and left entire coastal communities cut off by landslides for weeks. Many of those communities are still in temporary housing. The aftershock struck at a depth of 12 kilometers. It triggered new landslide warnings in already compromised hillsides. At least 3 structures that had been weakened but not fully demolished in the original earthquake reported additional collapse. Japan's meteorological agency updated its aftershock probability forecast and reminded residents in temporary housing near unstable slopes to monitor alerts continuously. That changed fast. What had looked like a region slowly beginning its rebuilding process was reminded, in 27 seconds of magnitude 6.1 shaking, that tectonic systems do not observe reconstruction schedules. To understand why 3 separate regions shook within the same short window, you have to understand what the Earth's surface actually is. The outermost layer of the planet, the crust and uppermost mantle, is not a solid shell. It is a mosaic of approximately 15 major tectonic plates and dozens of smaller microplates, all moving independently, driven by the convection currents of molten rock circulating in the mantle below. These plates move slowly, typically between 1 and 10 centimeters per year. That is roughly the speed at which your fingernails grow, but they do not move smoothly. They stick, grind, and lock against each other at the boundaries. Stress accumulates over decades, centuries, sometimes millennia. Then it releases all at once as an earthquake. Venezuela, California, and Japan all sit in tectonically active zones, but they are governed by entirely different plate systems. Venezuela's seismicity is driven by the Caribbean plate pressing eastward against the South American plate, creating a transform fault, the same type of fault that governs the San Andreas, where plates slide horizontally past one another rather than diving underneath. California's hazard comes primarily from the Pacific plate grinding northwestward against the North American plate along a system of faults running the full length of the state. Japan's seismicity is dominated by the Pacific plate subducting, diving beneath, the North American and Eurasian plates at the Japan Trench. So these are not connected in the way that a first glance at the headlines might suggest. There is no single rupture zone linking Venezuela to California to Japan. What they share is this: they are all located in regions where tectonic stress has been building for years, and they are all experiencing that stress expressing itself in the form of seismic events, some of which were already overdue. To put the energy involved in context, consider this. A magnitude 6 earthquake releases approximately 32 times more energy than a magnitude 5 earthquake. A magnitude 7 releases 1,000 times more energy than a magnitude 5. The magnitude 7.6 earthquake that struck Japan's Noto Peninsula in January 2024 released the energy equivalent of approximately 32 Hiroshima atomic bombs. This is not a figure designed to frighten. It is a figure designed to make the scale comprehensible. Because when you talk about a fault system like the southern San Andreas, which seismologists believe is capable of producing a magnitude 7.8, You are talking about an event that would release more than 100 times the energy of what Japan already absorbed. But here is the part that most coverage misses. The existence of elevated global seismic activity in a given window is a real observable phenomenon. The USGS tracks global earthquake frequency annually, and some recent years have shown elevated counts of significant events. But seismologists are careful, very careful, to distinguish between genuine trend signals and the natural clustering effects that occur in a system as complex as the Earth's crust. The planet experiences hundreds of thousands of earthquakes every year. Most are too small to detect without instruments. What feels like a synchronized global shaking event is often a matter of 3 newsworthy events landing close enough together in time to attract simultaneous coverage. What is real, and what scientists are actively monitoring, is the stress loading on specific fault systems. That is where the genuine risk lives. Not in a vague global pattern, but in very specific, very identifiable zones where the physics is pointing toward an overdue release. The difference between Japan's 240 deaths in January 2024 and the potential death toll of an equivalent earthquake in Venezuela is not luck. It is decades of infrastructure investment, building code enforcement, early warning technology, and public education. Japan's seismic preparedness is the most sophisticated on the planet. The country operates a nationwide early warning system that detects the primary waves of an earthquake, the faster, less destructive P waves, and broadcasts alerts to mobile phones, televisions, and public address systems before the slower but far more destructive secondary waves arrive. Depending on distance from the epicenter, this system can provide between 5 and 60 seconds of warning. That is enough time to stop a surgical operation, halt a train, open a fire station door, and take cover. Japan's building codes are among the strictest in the world and have been progressively tightened after every major disaster. Modern Japanese buildings are engineered with base isolators, essentially shock-absorbing pads at the foundation, and active damping systems that allow structures to move with seismic waves rather than resist and collapse. Even in the magnitude 7.6 January 2024 event, the death toll was concentrated almost entirely in older wooden structures built before modern code revisions. Venezuela has none of this. The country's seismic monitoring network has been deteriorating for years. At last published count, fewer than half of its original seismological stations remain operational, the result of budget cuts and equipment failures that went unaddressed as the national economy contracted. The early warning infrastructure that would exist in California or Japan, sensors, alert systems, public communication protocol, is largely absent. In Caracas and other northern Venezuelan cities, a significant portion of the residential building stock was constructed between the 1950s and 1980s under codes that did not anticipate the seismic demands now understood to exist along the Caribbean South American plate boundary. These are not just geological events. They are human experiences shaped by political and economic choices made over decades. California sits between these two extremes, but closer to the Japanese model than the Venezuelan one. The Shake Alert Early Warning System, developed by USGS, Caltech, the University of Washington, and the University of Oregon, now covers the entire West Coast and delivers automated alerts directly to Android phones and through the Wireless Emergency Alert System. In September 2023, Shake Alert issued its first public earthquake warning during a magnitude 4.6 event near Ojai, giving Los Angeles residents approximately 8 seconds of advance notice. 8 seconds is not very long, but 8 seconds is enough to instinctively protect your head. 8 seconds is enough for a surgeon to lift a scalpel. 8 seconds is enough for a driver to pull to the shoulder. And in a major event along the southern San Andreas, where Los Angeles sits roughly 80 kilometers from the most dangerous rupture scenarios, the warning-led time could extend to 40 or 50 seconds for parts of the city. The gap in preparedness between the best and worst positioned regions in the world is not a gap of knowledge. We know where the dangerous faults are. We know what the ground will do when they rupture. The gap is a gap of political will and financial investment. And that gap in the wrong place on the wrong fault is measured in tens of thousands of lives. So what are scientists watching right now? In California, the primary concern remains what seismologists refer to simply as the big one. The southern San Andreas Fault, which runs from the Salton Sea northward through the Coachella Valley and into San Bernardino County, last produced a major rupture in 1857. In that event, known as the Fort Tejon earthquake, the fault ruptured for nearly 350 kilometers, with horizontal displacement of up to 9 meters along portions of the break. Estimated magnitude, approximately 7.9. 169 years have passed since that event. The Pacific Plate continues to grind northwestward at roughly 46 millimeters per year. The stress is accumulating. The scientific community's language around the southern San Andreas is not if, it is when. USGS estimates there is approximately 60% probability of a magnitude 6.7 or larger earthquake occurring somewhere in the greater Los Angeles region within the next 30 years. For a magnitude 7 or larger specifically on the southern San Andreas, the probability window is estimated at approximately 20% over the same period. These are not alarmist numbers generated for headlines. They come from the 3rd Uniform California Earthquake Rupture Forecast, one of the most rigorous probabilistic hazard analyses ever produced for any region on Earth. Keep an eye on the Hayward Fault too. The Hayward Fault runs directly beneath some of the most densely populated areas of the San Francisco Bay Area, beneath Oakland, Hayward, Fremont, and the campus of the University of California at Berkeley. Its last major rupture occurred in 1868, producing an earthquake estimated at magnitude 6.8 that destroyed most of the city of Hayward, which was then the largest city in the Bay Area. Since 1868, the fault has been creeping slowly, not rupturing fully, just sliding incrementally, while stress continues to build in the locked sections. A rupture of the Hayward Fault today would strike a region with millions more residents and vastly more built infrastructure than existed in 1868. In Japan, the monitoring focus after the Noto Peninsula events has shifted to aftershock modeling and secondary hazard assessment. Geologists are tracking 17 specific slope areas in Ishikawa Prefecture that were identified as critically destabilized in the January 2024 event, and that absorbed additional stress loading from the most recent aftershock. The risk in these areas is not another major earthquake. It is rainfall-triggered landslides on slopes that have already had their structural integrity compromised by seismic shaking. Japan's Disaster Management Agency has issued preparedness advisories for the coming typhoon season, citing this intersection of seismic damage and extreme weather risk as a compound hazard scenario. Are all these earthquakes connected? Is something larger coming? Are we watching the early warning signs of a global seismic event? The straightforward scientific answer is no. The Earth does not produce coordinated global rupture events where multiple unconnected plate boundaries fail simultaneously. The physics of plate tectonics does not allow for that mechanism. The earthquakes in Venezuela, California, and Japan this week are not linked by a single underlying cause. They are the product of independent tectonic systems, each of which has been building stress on its own timeline. The supervolcano is not waking up. The ring of fire is not about to light up end to end. A globally coordinated seismic catastrophe is not what the science is showing. But here is what is real, and what you should actually be thinking about. The most realistic danger is not buried miles underground. It is not lurking in some global tectonic conspiracy. It is hiding quietly in very specific, very identifiable places. The unreinforced masonry apartment building someone you know lives in a California city that still has tens of thousands of them standing. The liquefaction zone in Seattle, where soil will turn to waterlogged slush during a Cascadia event. The Caribbean coastal town with no early warning system and construction that has not been inspected since the 1970s. The threat is not mysterious. It is specific, it is documented, and it is addressable. The gap between where we are and where we need to be is not a knowledge gap, it is a preparedness gap. And that gap is the story that matters, because that is the one we still have the ability to close. Go comment right now. Have you personally felt an earthquake? Tell me where you were and what it felt like. I read every single one. If this video added something to how you understand our planet, a thumbs up costs you nothing, and it helps more people find this kind of content. Subscribe if you have not already. We are working on deep dives on the Cascadia subduction zone, the Hayward Fault, and the structural vulnerability of older American cities, and you do not want to miss those. Let us go. See you in the next one.